I'm sorry, I didn't record any of that. This is number 16. There's a graph on it. Area under the graph is the work done. Boom. That's the whole thing. So we could do it that way and just find out the work done in the graph by doing the area under this curve. That would be 1/2 times 40 times 20. Those are in centimeters, so I'll put a 0.2 here to put our answer in joules. But that's going to be, let's see, 0.2 times 40 is going to be 8. Half of 8 is 4, so 4 joules. My math okay on that? So that's not the answer. The answer is going to require I go another step further. It says, what is the speed of the rock? So if we assume that all of this energy was then given to the rock as kinetic energy, then I would suggest that this changed the kinetic energy of the rock. And so my 4 joules would be equal to 1/2 mv squared. And the mass of the rock is 35 grams. So that's going to be 1/2 times 0.035 times v squared. I don't know the answer to that, but I know that's got to be what the answer is. Somebody want to tell me what that is, or I need to actually work it out? I don't really care what the number is. All right, don't worry about it. All of you can push buttons. So is there a part B to this? Nope. This is it. If I look at the answer, it tells me about 15 meters per second. So let's hope that works out to 15 meters per second. Pretty confident it will. All right. Again, that was number 16. Next question. Sir?
Can you go over 9.28?
So number 9 on mastering, which is number 28 at the end of the chapter. A 65-kilogram student is standing atop a spring in an elevator that is accelerating upward at 3.5 meters per second squared. The spring constant is 2,200 newtons per meter. By how much is the spring compressed? All right, let's unpack all of that. So why would Mr. Shelton assign this one? Maybe he just doesn't like his students very much, or maybe he just thought it'd be fun. But it sounds like some idiot brought a spring into an elevator. So is this what we got? What's the problem with that? It's no longer Inktober. I don't have to worry about my drawings as much. So don't shame me. The elevator is accelerating upwards at, what'd they give me? 3.5 meters per second squared. I'll tell you what, that'd be an uncomfortable elevator to ride in. And that's a heck of an acceleration upwards, just so you know. I don't think you would enjoy it very. Now, it'd be like, who's been on one of those turbo elevators? Do you guys know what I'm talking about? Like the ones that go in high rises? You know, and those might have a acceleration near that. Most of them don't. Most of them don't accelerate near that. We're talking about maybe 1 meter per second squared, and they only do that for an instant. They get up to a relatively slow speed, and then they stay there. So they tell us that the spring constant is 2,200 newtons per meter. That suggests the net force on the person is not balanced. This has to be done as a Newton's law question. And the normal force upwards is going to be greater than their weight downwards. That's going to equal MA, and they are accelerating at the same rate as the elevator. Now, the normal force on them is from the spring. I don't really think I have to talk about that too much. And I don't think I need to convince you that the normal force is equal to Kx for the spring. Is that okay with all of you? Do you need more than that for an explanation? All right. So Kx equals mg plus ma. We're probably looking to see how much the spring is compressed, I bet. Yeah, so we have the mass of the person, I'm sure, 65 kilograms. This is mastering, so they probably use 9.8. And the spring constant, 2,200. That's going to be what x is. I don't know, half a meter. Somebody work it out. What's that? All right. I don't know what this works out to, but my assumption is that it's not more than a meter, just looking at the numbers. So,
My numbers were different, like from,
oh, you guys had different numbers?
Yeah, I have different ones.
same thing though.
I usually uncheck that box, but I might have missed it.
I just wanted to see how you did it.
That's how I would do it. Now, is that the only thing in this question?
I think so.
Yeah.
That's too bad. I would hope the follow-up would have been how much energy is stored in the spring. But it's not there, so don't worry about it. Yeah?
13.
13. The amount of work done by this force would still be F dot delta X dot cosine phi, where delta X could be, say, this distance along the ramp, okay? Now, for it to be moving at a constant velocity, it would have to be true that this component of the force equal whatever components of force there are in this direction. That could be friction, it could be mg sine theta, it could be some combination of that. But even if we say it's frictionless, where this would make this mg sine theta, to calculate the work done by this force, I would still need to take this angle into account. Now, saying all that, I also know that if it's moving at constant velocity, mg sine theta has to equal F cosine phi. That would have to be true because this is the part that's pulling it up the ramp. This is the part that's being pulled down the ramp, and it's moving at a constant speed, so the net force is 0. But still, if I wanted to be strictly interpret the way in which we're supposed to do this, that would be the way to do it. Now, I'm saying this trying to be very clear to answer your question. Let's say we're told that there's some force pulling the box up the ramp. Now, the only way we know that that happens is if the component up the ramp is equivalent to that and that plus friction. So you could solve this without knowing this angle if you knew that it was constrained to move along the ramp, because you could figure out how much of this force is in that direction by an indirect method. Now, you guys who are only giving this like a passing listen, I would be willing to bet you this is worth writing down. I'm not saying this on your next quiz. I'm saying this speaks to your understanding of how this is supposed to work. And I've written all sorts of garbage here, so let me clear this out, make this a little cleaner. Okay. Let's say that I tell you that this is 40 degrees, and I don't tell you phi, but that the box is 10 kilograms. And I say that it's moving up the ramp. I could ask you, without telling you what this force is, and without telling you what this angle is, how much work is being done by that force. And you have enough information right now to answer that, even though you don't know that force. Is everybody paying attention to that statement? The only way this box moves at constant velocity is if the net force is 0. This also means that the box has a net work of 0 going from A to B. So if I want to find the force done by this force, I can use any method I want. That doesn't mean I can have to use F cosine phi delta X. If I don't know what F and phi are, I would need another method to find out how much work this is. One way would be to find out what component of the work is in this, what component of the force is in this direction. That would be okay to do. I know what component of that force has to be in that direction for it to move at constant velocity. It has to be mg sine theta. The only way the box moves up the ramp at constant velocity is if there's a component of the force that balances the weight down the ramp. So I don't have to know the size of that force or that angle. On the other hand, if I don't know the network is zero, if I don't know if it's going up the ramp at a constant velocity, then the problem becomes far more challenging. I would have to know something else. I'd have to have something that can clue me in as to what this force is actually doing to the box. Like they could tell me that it's accelerating. They could tell me what the change in kinetic energy of the box is. They could give me any number of things. I mean, because there's work being done by two forces here. There's three forces here. There's work done by that applied force, plus there's work done by the normal force, plus there's work done by gravity. And if that's zero, then the box is moving at constant velocity. If it's not zero, that equals the change in kinetic energy. Now, I've really not talked about it in this way. But when we're tracing energy, and that's essentially what's happening here. When we're tracing energy, you are responsible for knowing two things, and I think these are kind of challenging to kind of put together in your framework. One, you need to account for all forms of energy that could exist in the system, both adding to the energy of the system and taking away. But second, you need to be able to find indirect methods of getting the work done. And that's much harder. Because for you guys, it could be anything. Where do I even begin? There are some clear places to begin. And net force isn't a bad place to think about when you start to begin. What do you know about your system that will help you identify how much work is being done? I mean, I never put this down specifically, but net force equals zero means net work equals zero. That will always be true. But net force equals MA means net work equals change in kinetic energy. That will always be true. So it also follows that if there's any change in kinetic energy, we know that there was net work done and the net forces were unbalanced. Does that help?
Yes, it helps, although.
A little.
If I answer what I was going for? Okay, so.
That's what I was worried about.
The answer for 6B was negative weight sine theta times L. Because the force was.
That's all right. Hey, folks, before you walk out.
Negative weight sine theta, and it's negative work because it's going in the opposite direction.
Okay, you said B. What is the work done by gravity?
Yeah.
And move the distance L up the ramp.
Yeah.
Okay.
Okay.
And your question, I'm going to just draw it again. Your question was, because I didn't answer it.
My question is because we already have the sine theta taking into account that is the component, is that specific component of gravity, we don't have to then do cosine theta. Because like the equation is F change in X cosine theta. Since we already account for the direction once.
I hear you.
Component, we don't have to.
Yes. That is a true statement. And for everybody else to understand that statement, I can write this answer as this is 90 plus theta. We played this game in this class or fourth period yesterday. It was not a fun game to play, talking about all the different ways that these angles are related. I did not enjoy it because I am not a pre-calc teacher. So if you watch the video, skip that section. It's horrible. But a lot of people have no idea the relationships between these trig functions. But right now, mg cosine 90 plus theta times L is the work done by gravity. This is negative because a cosine of 90 plus theta will be a negative answer as long as theta is between 0 and 90. But this is mathematically identical to mg sine theta times L with a negative sign out front. These are mathematically equal. And the reason is because cosine 90 plus theta equals minus sine of theta. And I'm afraid that's not particularly well known. In fact, how many of you know these identities? Okay, that is clearly not enough of you. I don't believe this is a huge thing to run out and learn, but I tried to explain it in fourth period, and it was a disaster. Mostly because I wasn't prepared to go over it. But I think almost all of you know that sine of an angle is equal to cosine of its complement, and vice versa. You know the minus ones, right? The plus ones are similar. I'm looking around the room and it's clear that that is not true. All right. Look, I want you to know these, and I'm going to show you how to learn. All of that was to try and just help Melissa with her question here. Not a bad question. But knowing that these are mathematically the same and recognizing it, I don't know if they'll accept this as an answer on the exam. You might need to be able to do this. They're going to assume you've had pre-calculus and calculus. And if I were you, I would write these down. It might never come up, but I want you guys to be smarter than the average bear. The easiest way to learn these is to remember the sum and difference formulas. You guys learned these, right? Okay, I guess I said it to the air. Did you learn these?
No, I didn't.
You've never seen these before?
Sure I have.
Yeah, it becomes really easy until I actually ask you to do something. So how do you think the next one is different? It's not a huge deal, right? Probably a big minus right there, right? Now these ones, these escape me usually. Isn't it cosine A cosine B plus sine A sine B? Is that right? I haven't seen these in a long time myself, but I at least know they exist. Ah, I blew it. I can't remember. Is it a minus sign on this one? Is it reversed? Because I'm pretty sure they reverse them. It's been a long time. Because the implications is all I care about, but this is what you use to solve these problems. So, cosine of 90 plus theta. Grab the plus formula and just substitute in. You're going to get cosine 90 times the cosine of theta minus sine of 90 sine of theta. Well, cosine of 90 is 0. That whole term goes away. And you're left with minus sine theta, since sine of 90 is 1. I tried to explain it by drawing the triangles, but full-blown lost everybody in fourth period doing that. Tried to explain it using this in this class, but it only works if you know these. But I think you guys can figure out the rest of them now on your own, right? Look. All right. Sounds like we're done with the homework. If I was to give you a quiz, first 2 minutes of class tomorrow, to me, this is not a problem. Say I have a 10 kilogram block and a spring of 1,000 newtons per meter and a coefficient of friction of, say, 0.6 all along the surface. If I pull the block back, say a distance a half a meter, how much energy is in the system? And where does the block come to rest? Now, it's incumbent upon you to realize that there is a really hard way to do this question and a really easy way to do this question. So I will tell you what I want you to do. I want you to figure out this answer using nothing but the definition of work. You should follow the flow of energy. When the object is here, the energy is in the spring mass system. The problem will progress until the instant the spring is back in its relaxed state. At this moment, some of the energy is now with the block in the form of kinetic energy, but some work has been done by friction, moving the block to here. Does everybody understand why that had to be true? A frictional force acted on the block. The frictional force was in this direction while the block slid forwards half a meter. The block then continues until it reaches a point here where it stops. That point where it stops is the point where all the kinetic energy has been taken away by work done by friction. If you're careful, this is a two-line problem. I'm not trying to fool you. There's work done on the spring, and all of that work will be then done by friction. If you trace the energy, you can do this in two lines. Please consider looking at this problem tonight for homework. Tomorrow we're going to I think all of you know what problem I'm speaking about right now. True? I'm going to be very, very clear with you. And I even posted this on Edsby. Did you guys notice? I'll start doing that. I'll take some notes for you and just post them. Things I think you should know. There's nothing there that isn't or hasn't been discussed in the notes, except for the last 2 or 3 because they're on stuff we haven't covered yet. But if this box moves at constant velocity, then net force is 0, net work is 0. Now what this really means is that the work done by the pulling force plus the work done by the normal force plus the work done by gravity has to equal 0. Has to. Right? Those are the only 3 forces that could possibly doing work. In the same way that if those forces are unbalanced, then the net work must equal the change in kinetic energy. Again, that would suggest that the pulling work plus the work done by the normal force plus the work done by gravity has to equal the change in kinetic energy. These all have to be true. The person was asking a specific question about the work done by gravity. and asking if it's okay to write it in terms of the component of the weight. Meaning, can I write the work done by gravity as mg sine theta times L? And what she was really asking is this okay for the work done by the pulling force? There was some force, I think, acting this way. And is that a correct expression for it? I don't know, is it?
Yes.
Now, I could say that the work done by the pulling force is F times L. That would also have to be true. Is there a reason to believe these two are equal?
Yes.
And the problem there is, because we know that in the problem, the object moves at a constant velocity up the ramp. And we know that the work done by the normal force has to be 0. So the work done by the pulling force would have to be equal and opposite to the work done by the gravitational force. And yeah, it's true that there's a component of the weight down the ramp, which we know is equal to mg sine theta. On the other hand, the work done by the gravitational force could also be based on this angle, and that would be mg cosine 90 plus theta times L. Are these equal? Sure. This is explicitly negative, though. It's explicitly negative. But we know that this and this have to be equivalent. Look, none of these ways of looking at these problems are wrong. They're all correct. If you know the work done by 0, there's absolutely nothing wrong with getting an indirect answer for the work done by the pulling force. Nothing wrong with it. Meaning we're getting it indirectly by looking at the work done by gravity and knowing the normal force is 0. Look, you're using your physics. That's how to do this. In fact, that's the efficient way to do it. It wouldn't matter even if, instead of having it look like this, what if the pulling force was if the box is still moving up the ramp at a constant velocity, then this would still have to be the work done by that pulling force. It would have to be. Right? Because it's only that component in the direction of motion. So I want you to understand that once you understand the way these things are connected, you can use them in any combination to get to the answer that you're being asked. Look, this is not what's going to be on the exam. This is not going to be how I want you to use this. This kind of homework you're doing is just to make sure you understand the basics, that you understand what to me is probably the least important part, which is the mechanics of doing the calculation. That's all your homework questions ever really ask. They never really ask anything outside of that too much. The tutorials do a little bit, but not enough. A lot of times it's simply the mechanics of the calculation. You got to nail that stuff. You can't make mistakes there. Because being thoughtful about the answer, that's going to be harder. All right. Go ahead. Now, this is exactly where we finished just yesterday. So here's, that's not here it is. Here's object 1. It's number 15. Object 1 and object 2. First, I want to make sure you remember the gravitational potential energy between any two objects is minus m1, m2, g over r, their separation distance. Now, we're not told if they're brought closer together or further apart. But this is the potential energy. The work done in bringing an object from infinity to any point in space is m1 m2 g over r. It's positive. That's the work done in bringing an object from infinity to a place. So let's say this is our reference point, this little x over here, and we're going to bring our object from x1 to x2. We want to know how much work is done. Okay? So, the idea here is the work done will be this is the work that represents the amount of energy required for the object to go from infinity to x1. And then we moved it from x1 to x2, so that's the work to bring it from x1 to x2. Now that's not really the best way to do this. The best way would be to subtract the works outright. If you really want to see what I should have done explicitly, and some of you might want to see this, but not many of you, is I should have gone the integral from two integrals, from infinity to x1 and then x1 to x2. That's technically what I should have done. But I think you guys understand that once I realize that this is the work done in going from infinity to a location, subtracting that amount of work will give me how much work is done in going from one to the other. So it would be m1 m2g over x2 minus m1 m2g over x1. Please note that by definition, and the way I've drawn this number would be a positive number because x2 is smaller than x1. Thus, 1 over x2 minus 1 over x1 is inherently positive. You guys all okay with that? Any question about why that's true? Okay. Now, this suggests that if I just let this object go, but held this object in place, I'm sorry, that's wrong. If I just, I gotta get my eraser out. If I just let this object go and held the other object, which is not pictured, in place, and it moved from here to here. I guess I drew this all the way wrong for all of you guys. Huh. I totally did. Totally did. And luckily no one was, kind enough to tell me that from the beginning. So I'm just gonna act like I drew this different, and then you guys can, when the class is over, go out in the hallway and talk about how Mr. Shelton's an idiot. And I won't feel as bad about it because it didn't happen here. Object 1, object 2. I guess this is the way I should have drawn it. There. Because there's two objects, but one of them moves from one distance to another. Or they both move in. I don't know which. It's not clear in the question. So I guess that's more what's happening. What I was going to try and get to here, and I obviously didn't, is that if I hold object 1 in place and I just released object 2, that object 2 would move to this location and would now have had this much work done by gravity, pulling it to the new location. The work done is positive, suggesting that this would equate to a change in kinetic energy of object 2. That's what I wanted to be able to say. Meaning, if I just let this object go, it would naturally be pulled by gravity to this location, accelerating the whole time. Just like if you drop something above the surface of the earth, it would naturally fall towards the earth, accelerating the whole time. So that when it gets here, it would have some velocity that it didn't have before. And that velocity would be based on that amount of work causing a change in kinetic energy. It's probably not what would actually happen. That question. Okay? I mean, you can put the numbers in, right? Good. One little thing, though. When they said one mass stayed in place, if it was mass 1 that stayed in place, this is the kinetic energy of object 2. And this m represents the inertial mass of object 2. That's why it's there. How much kinetic energy it receives is based largely on how much inertia it has. Objects with more inertia are more difficult to accelerate and therefore harder to give energy to. And it shows up in the calculation for kinetic energy. All right. Another question on the homework? See if I can put that one too. Let's see. I did this here, and I did such a bad job on it in third period. I think what would actually happen is object 1 and object 2 would start this far apart. When released, they would be this far apart. They'd experience a mutual force of attraction. But now that they're this far apart, they're both moving. There would be a change in kinetic energy. And by the way, those of you not realizing that this is a little bit of new information, it's a little bit of new information. But I don't think it's that new. I don't think you guys really have a lot to worry about here. The amount of work would be m1, m2g times 1 over x2 minus 1 over x1. That's how much work would be done. But now, that's changing the kinetic energy of the system. If the objects were at rest, the change in kinetic energy would be 1/2 m1 v1 squared plus 1/2 m2 v2 squared. There'd be no way to easily know how fast they're going or even how fast their closing speed is. Right? Too many unknowns. Even if I knew m1 and m2, this alone would not allow me to get v1 and v2. It works nice if I hold one in place, but that's an external force acting on the system. Now, to me, this is going to be a more interesting question, but believe it or not, you guys who had physics last year should know how to get the answer. I know you're thinking you don't, but what was the momentum of the system before I released it? Do you guys remember the term momentum? Momentum is just mv. If neither object was moving before I released it, what was the momentum of each object? So there was no momentum in the system before I released it. That suggests that there's no external force acting on the system. And there isn't. This is a Newton's third law force, so it's an internal force. Then the momentum of the system would still have to be 0, suggesting m1 v1 plus m2 v2 equals 0. These rules are not meant to work in isolation. These rules are meant to work together. Momentum is a powerful rule and a powerful law. It's more powerful than talking about energy because it has no exceptions. And there's only one way to measure momentum. So in this problem, energy and momentum are needed together to figure out what would be happening. What would be their speed right before they collide? Something like that. This is an excellent question. It has lots of far-reaching goals. This is the amount of work done and the change in potential energy. Well, there's more to this question, probably. If one mass is much greater than the other, the larger mass stays essentially at rest while the smaller mass moves towards it. Suppose a 1.5... All right, well, I kind of showed you how to do that, so I don't think I have to do that now. Are we good? One mass essentially stayed in place was